So be short, do one thing, have few arguments, have a consistent level of abstraction. Code Climate does all these things for you. But let me make this concrete by actually showing the evolution of some code that I wrote that started out violating single level of abstraction. And after a couple of refactorings, I managed to get it there. All right, so hold on. Sorry, these are a little bit out of order here. I don't know how that happened. Basically, if you're going to be a programmer in some language, the refactoring book for that language ought to be permanently on your bookshelf somewhere. Basically, each refactoring is the name of a condition to look for, like some problem with your code, a smell that manifests in a certain way, a recipe for how to solve it, usually by applying steps that are almost mechanical in nature, and then some examples of that in real life. So you think of these sort of like cookbooks, right? You kind of have to know what you're looking for. But I'm going to give a couple of examples that use some very basic refactorings that I'm guessing probably all the projects in this room, these would be applicable to some of the code that you write. So hopefully this will make the single level abstraction thing clear by example. And this is based on some actual code in an app I wrote that, in fact, one of the teams is working on some features for. In this particular case, the code in question is supposed to do the following thing. Theaters want to have people on their mailing lists. Sometimes people opt out of the mailing list, which is legal, and you have to give them the ability to do that. And what the code is supposed to do is that each time you log in, if you have previously opted out of the mailing list, there's like this little polite message that invites you to opt back in. That's all it's supposed to do. So the original version of this was when you log in, the first screen that you hit is the one that's defined by the show action in the customer's controller. So in the show action, this is where the logic is supposed to be that does the test I just described. And again, if you try to read the code and it's confusing, that's the whole point, right? The point of this example is here is a bunch of code that makes a bunch of mistakes. First of all, it mixes the thing to be done with the idea of how to do it. So there's something called a blacklist, and there's an idea of a user having a valid email address. You're supposed to somehow figure out that there's maybe an admin settable option that turns this entire behavior on and off. But it's not clear from looking at this code what it is supposed to do. Why? Because the code is actually showing how to do it, but it's not very expressive about what it's trying to do. And in fact, there isn't even a comment here, but even if there were a comment here, I would contend that it's still bad code. In fact, the extreme position is if your code is really good and self-descriptive, you almost don't need comments. So what are the problems with this, and how did, by the way, this code no longer exists in the app. It got refactored, and I'm going to show you how it got refactored. So one problem here is that the code is mixing levels of abstraction. What does that mean? That there's the notion of a valid email address. Well, you can sort of figure out what that is, right? And you can imagine that somewhere there's this function called valid email address that figures that out. You don't know how it works, but it's pretty clear just from looking at that line of code that what it's checking is, does the user have a valid email address? So that's what to do. On the other hand, there's also this e-blacklist. We're not sure what that is. And there's this option value thing, which, again, it's showing how to do something, but it isn't clear what is being done. So whenever you're kind of reading code, and there's some parts of the code that seem to be expressing how to do something, but other parts are exposing implementation details about how to do it, that's kind of the yellow flag that you might be mixing level of abstractions. And it also turns out that there's a logic bug here, which is we actually want to do it only once per login. And it turns out that this does it multiple times. This is the version that ultimately made it into the code base. And it got split up into a couple of different helper functions. So one helper function is called login message. And its job is, if the current user has opted out of email, it will give him the helpful, encouraging opt-in message. Otherwise, it gives you back a blank, right? But notice that this function does no longer mixes levels of abstraction. The login message function is exclusively about saying what is to be done, not how to do it, right? In particular, current user has opted out of email. This function hides the implementation of how we determine that, right? So If it turned out that opting out of email is no longer something you look up in the database, but something that you'd have to compute, doesn't matter, because from the point of view of this login message function, it hides the implementation of how to do that thing. It just says what it wants done. Similarly with encourage opt-in message, that is a function call. How does the opt-in message get generated? We don't know. But it doesn't matter, because at this level, it's very clear what's happening, right? Encourage opt-in message if current user is opted out of email. You can almost read it like a sentence. So it hides the details of how each one of those things is done, and it focuses only on what is being done. And then, in turn, we're going to have a different set of helper functions that focuses just on how to do each of the things. So here's one of them. The encourage opt-in message function is the one where now we're looking at the admin settable options, and assuming that the admin has turned this option on, then we have this friendly message. But the point of the example is, if you don't care about how this message is generated, you never have to look at this function, right? The function hides the implementation of something while giving it the function a revealing name to tell you what is being done. Similarly, I got to scroll down a line or two. Similarly, the idea of, let me get this out of here. Similarly, the idea of has opted out of email. So what does it mean for someone to have opted out of email? Well, it turns out in the current implementation, if somebody has added themselves to the blacklist, which is a box they can check, that's a database field, and if they have a valid email address. So opted out of if you don't have a valid email address to begin with, you can't opt out of email. So it's not meaningful to ask the question, right? Those people should never see the reminder, because there'd be no way for them to opt in if they don't even have an email address. So, but again, what's the point here? The function name tells you what is to be done, but it hides the implementation of how to do it. The implementation is buried down here. If the way that we computed opting out of email were to change, only the interior of this function would change, but nothing above this line would have to change. In particular, the logic we originally cared about, which is that this whole workflow is triggered only in the case that the customer has previously opted out, now looks just like this. Right? So basically, we've hidden the implementation of everything below this point. It's like a news story. If all you read is this function, then you know that whenever the login message function is called, it will generate a message that is either the opt-in message if the user is opted out, or else it's going to be blank. But nothing about this function says how those things are done. If you care about that, for example, if you want to change the text of the message, or you care about the implementation details of what opting out means, then you can go look down in the helper functions and figure that out. Right? So it's a simple refactoring, but it actually ends up having a number of nice benefits. Oh, come on. Where are you? So besides the fact that arguably the code is easier to read, because now it's sort of structured top-down, where like the top function is just a summary of what's going to happen, and the helper functions that it calls do the work, it's also arguably easier to test. Right? If you recall in the original version, oops, that's not mirrored again, sorry. This was the original version, right? Think about how you would test this. Think about the number of things that you would have to stub or mock in order to do a reasonable test of this piece of code. First of all, it's hidden inside a controller action, so that's kind of already a red flag, right? Controller actions should be pretty concise to begin with. But whatever self.currentUser returns, presumably it returns some object representing a user, you have to make sure that if you're using a mock object, that it can respond to eBlacklist, that it can somehow respond to or make a call to valid email address. You have to figure out what this option value thing does and ensure that that option is available. So the number of preconditions that you have to establish just to call this piece of code and do some kind of a test on how it's behaving is already pretty daunting. And by the way, that is one of the very best indicators that your code is too convoluted. If you're trying to write a test after the fact, and I know that we always tell you write the test first, and I try to write my tests first, but I would be lying if I said that I'm 100% faithful to that. Sometimes I do write a little bit of code, and then I write the test after. But if you find yourself writing a test and having to stand on your head to set up the preconditions just to call the code to be tested, that is a really good sign that it's crying out for a refactoring, that you have mixed different levels of abstraction and you have a piece of code that is trying to do too much. Whereas in the refactored version, right, encourage opt-in message can now be tested separately. The only thing it really does is look up the value of an option, and depending on that value, it either generates a message or not. That's really easy to write a test for. Yes?
Yeah, you put a lot of the code in the application controller in the refactored version. I'm wondering, like, what is supposed to be in that file and what is left still in the customer controller after this?
OK, that's a good question. I'll get right to that. Similarly, for has opted out of email, if you wanted to test whether this method does the right thing, all you're really doing is testing the conjunction of two conditions. You could decide to stub one of them out or not. And each one of these is actually testable. Well, this is just a database attribute. But valid email address is already its own function. You could have separate tests for that. So basically, the other value of refactoring is you can break things into individually testable pieces. Right? You're essentially testing each helper piece rather than trying to test the whole thing at once. The question that was just asked was, in the refactored version, why is it that I put some of this code in application controller rather than putting it in customers controller? The reason here is that for reasons too complex to currently explain, these helper methods are actually used in a couple of different controllers. And since all controllers inherit from application controller, putting the logic there allows it to be called from any controller pretty easily. And by the way, I need to refactor that too. The truth is that this code should really only be in one place for logins. And then it would just live in that controller, and that's all it would ever be. But that's the reason in this example. It's all other controllers inherit from this. So little bits of functionality that many controllers want to share can be put into the application controller superclass. That's the only reason. Good question, though. Let me do an example that's a little bit more meaty and is actually based on real life. And by real life, I mean a commercial product, not my code. But the strategy is basically the same, right? You start with code that has one or more problems or smells. It might be too complex. It might mix levels of abstractions. And through a series of small steps, you transform it to code that, from which those smells are ideally absent. And at each step of the way, you sort of are doing some testing to make sure that the breaking apart that you're doing actually behaves the way that you expect. And that means that anytime you modify code that has existing tests, you're probably going to break something. So think of it as you're trying to get from stable point to stable point. A stable point is your tests are all passing, but your code is ugly. You're going to make some changes to improve the structure of your code, but you don't want to change its behavior. So in that intermediate moment, your tests will no longer work, right? Because your tests, especially if they're unit tests, may make assumptions about the implementation, and you're about to change the implementation by refactoring. As soon as you do that, you go back and adjust the tests so that they match reality of what your new code does, and now you're in a stable place again. So basically, you're trying to minimize the time that your tests are read. And the example that I'm going to show is based on, does anybody remember this product? At one time, this was going to be the product that killed off the iPod. How many people actually recognize this or even recognize the name Zune? OK, roughly a quarter, maybe not even a quarter of the hand. So that's how successful it was at killing off the iPod. However, it turns out, and this is a real story, that as packaged, the Zune had a problem that if you booted it up on December 31st, 2008, which was shortly after the product was released, it would brick as it booted up. And after a fair amount of investigation, Microsoft posted the solution on the Zune website, which was wait until the morning of January 1st, 2009, and reboot it. And that would fix it. So the question is, what is it that made that happen? The code that I'm going to show now, we're going to walk through a refactoring of that buggy code. Do not worry about taking notes on it, because all of the code is available on GitHub, and every intermediate step that I'm doing is part of the GitHub repo with annotations. So I'd rather sort of make sure people understand what the process is. Here is a transliteration of the code that caused this real-life problem in the Microsoft Zune. The problem was ultimately traced to a piece of code that at boot time is supposed to figure out what today's date is. And the way it did that is that it would, taking January 1st, 1980 as being day 0, there was an internal clock chip that told you how many days have elapsed since that day. So the idea was start from that number and figure out what today's date is based on that. And in particular, this is a transliteration of the original code, which I believe was posted in Java. All I did was translate it to Ruby. So it contains the same bug that the real code contained and that caused it to freeze. And to demonstrate that bug, we have these RSpec tests. OK, so let's deconstruct what is my test case trying to do. Question? Is there a question? I can help. No? Question? Clarification? You guys need clarification on something? OK, I guess not. So here's a set of tests that you can imagine if you were putting together some simple unit tests for this function. Basically, I'm saying, OK, I'm going to have a list of pairs where in each pair, the first number is number of days that have elapsed since January 1st, 1980. And the second number in the pair is what year is it now, given that. So if 365 days have elapsed since January 1st, 1980, that means today is December 31st, 1980. If 900 days have elapsed, then it's sometime in 1982. If 366 days have elapsed, then it should be the first day of 1981, and so on. Right? So all I'm doing is for each pair of numbers, I'm just saying if I call the convert function with the first number, what I should get back is the second number. Easy enough. Right? So suppose I run that. Sorry, let me get rid of this silly window here. OK, I'm going to run it. So what's going on here? Well, let's see. Green test case. 365 days puts us in 1980. That worked. 900 days puts us in 1982. Looks like that one worked. What's happening with, like, why am I not seeing green or red for 366 days should put us in 1981? Because I have triggered the bug that if this were a Zune hardware device, would have just bricked it. Right? Basically, there is a condition in which not only does the function not do the right thing, but it hangs up. It goes into an infinite loop. So let's take a look at some refactorings that you might do to make this work a little bit better. If you were sort of taking a test-centric point of view, this function mixes up a lot of stuff. There's a lot of problems here. First of all, there's quite a bit of complexity. Right? Just look at how much indentation there is. There's a while loop. And inside the while loop, there's an if. And inside the if, there's also another if. So by the time your brain gets to else, just remembering where you are in the flow is already pretty complicated. This is something that would show up as both a cyclomatic complexity issue, because there's a lot of paths through the code. Guys, if you're going to talk, I'd really rather you don't do it in here, because it's actually extremely distracting to try to talk over you. Thank you so much. Great. Where was I? So just the number of levels of indentation suggests that it's actually pretty hard to keep track of where the code is. There's also a lot of magic constants scattered in here. Although, if you know something about years and leap years, it might occur to you that 365 and 366 and the modulo 4 and modulo 400 calculations might have something to do with figuring out leap years. Because if the goal is to compute what year is it now based on how many days it's been since January 1st, 1980, you have to account for the fact that some of the years during that interval might be leap years, right? So that's basically what this function is trying to do. It's trying to sort of peel off a year at a time until the remaining number of days gets below 366. At that point, that's the year that you're in, right? So that's basically what the function is trying to do, but it's trying to do it in a way that almost but not quite works. And the first refactoring you can do, so here's one simple refactoring. There we go. See if I can make these both actually, let's see if I can make these both visible that way. That might be better. Cool. Get out of here. OK, so what's the first refactoring that I did? Well, I'm guessing that that first set of if statements has something to do with figuring out if the year is a leap year. And by the way, most people get the leap year calculation wrong. For those of you who care about these minutiae, if it's a multiple of 4, then it's a leap year, except that if it's a multiple of 100, which also happens to be a multiple of 4, then it's not a leap year, except that if it's a multiple of 400, then it is. Everybody get that? Okay, so a leap year is every 4 years, except if it's a century, but yes, if it's a 400 century or a quadricentennial or whatever that is, right? So by that recollection, 1900 is not a leap year, but 2000 is a leap year. Figure it out. Anyway, those are the rules. So the first step was just to sort of factor out that logic, right? And that's easy enough because I just have a function leap year, and I can test that function separately, right? I can find someone who is a leap year expert, have them devise a few test cases and say, yep, that's all the logic. And I've done a little bit of simplification because now notice that I'm trying to move this top level function towards saying what is to be done, and I'm trying to move away from saying how to do it. I'm trying to move the how to do it part into helper functions. So the first method that I have extracted, as we say, is I've extracted the leap year method into its own thing. And by doing that, one immediate benefit is that I can test that method separately, right? So I have also made this thing its own class. And I'm going to use that fact later so I can make some instance variables. But for now, I just have a simple set of tests that gives the sort of 3 boundary conditions, which is every 4 years. Okay, that would make this a leap year. It would mean that centuries are not leap years, but centuries are leap years if they're every 400th year. Right? So it's a really simple set of test cases, but it buys me some coverage, and I can actually run those cases. That's cool. All right, so I've got 3 passing tests that cover that 3 simple functions. But I can go a lot further with refactoring. So let's ping pong and go back to the other window here. Here's another version. So what have I done in this version? First of all, I have just accepted the fact that this date calculator, or whatever we want to call it, let's just make it a class. And one of the things when we start talking about good class design, which is later this week, a good class should have only one set of responsibilities that's very tightly coordinated around each other. So this class's responsibility is to do this calculation of converting days to what year it is. And by the way, that means that if I have a class, I can now talk about an instance of the class. So in this case, the things we're keeping track of are how many days since the initial day and what the initial year is. So I can just capture that. I can encapsulate it in an instance of date calculator. And now I can use the instance variables all over the place. So I no longer have to pass any values around. That's pretty nice. Here's my original convert function. And now look how much closer to the intent of the code I'm trying to get. Now the top level function just says, while more than 365 days remain, then if it's a leap year, I'll add a leap year. Otherwise, I'll add a regular year. Again, this says nothing about the implementation of those, right? This is just the what is to be done. And down here, we have extracted all of the methods for how to do it. In particular, leap year we already saw. We did that one over there. What does it mean to add a leap year? It means that, and here's a hint, this is where the bug arises, that if the number of days remaining is greater than 366, then we peel off that many days and we add a year. What does it mean to add a regular year? It means that we subtract the number of days in a regular year and add a year. So I'm a lot closer in the convert method that if you just read it, now it's kind of clear what it is trying to do. If we look at the tests for this refactored version, what could I test about it? Excuse me. So here, all I've done is change the way the tests are implemented. I'm not actually adding new tests yet. I've changed how the tests are called because I encapsulated all of these things in there into a single class. And finally, if I now add, here's where I've added the tests. Here we go. OK. So here's where I'm adding some tests to test these newly extracted methods. Right? I have add leap year, add regular year. Because those are now separate methods, I can test them separately. And in particular, I can now isolate the cases where, for example, if there's not enough days left in a year, so if the number of days remaining is less than a year, then I can say, I'm going to start with the year 2008. There's less than a year's worth of days left. Therefore, if I call add leap year, nothing should happen to the year. See how the test is written? One more time. Because I've encapsulated the date calculator into its own class, and I can specify what the year 0 is, the year corresponding to day number 0, I'm going to say that that year is 2008. I'm going to say that it's been 225 days since 2008. So if I try to call the add leap year method, nothing should happen to the count of years, because there aren't enough days remaining to make up a year that I can peel off. And you can apply a similar argument to the other tests, which is if there is greater than a year of days left, so 400 is clearly more than a year, in that case, if I call add leap year, and knowing that 2008 is in fact a leap year, then I would expect that the year actually would change. And then finally, the boundary case, which is that if there's exactly a year of days left and it happens to be a leap year, so 2008 was a leap year has 366 days. So yes, in this case, if I call add leap year in this example, then it actually should increase the year by 1, because that was a leap year. Fair? All I've done is extract the logic for what it means to peel off a year or peel off a leap year. And in individual cases, I'm isolating, does that logic do the right thing kind of at the boundaries, right, where it's exactly a leap year? So what happens if I run those specs? Let's run those. Oh, sorry. OK. So hold on. There we go. So the version of the refactoring I did actually obscures what the original bug was. Let me find here's the version that we started from. So here's the original version. The original version has, inside this inner if clause, it has d greater than 366. The add leap year function here, actually, if I was being really honest about how this worked, I would have left this as is, right? Because the add leap year function corresponds exactly, right? This code is exactly the code inside that nested if statement, right? That is just, literally, all I did is take that code and I moved it into its own function that I can test separately. So if I really copy the code, I should have copied d greater than 366. I've now changed this to match in order to illustrate the point that if I run that version, the peel off leap year function actually no longer does what it's supposed to do. In fact, it's saying that in the case where, there's add leap year. In the case where it's a leap year and the number of days elapsed is 366, which is exactly the number of days in a leap year, then when I call the add leap year function, it actually should increment the year, and the test is now claiming that that didn't happen, right? And that's because in my extracted code, I actually replicated the bug that happened in the original code. I guess it would have been more dramatic if I had left the bug in initially, right? In this case, if I fix the bug, right? So the problem with adding leap years is that to say that it's a leap year is not to say that there are more than 366 days remaining. It's more than or equal to 366 days remaining. That's what would cause the bug to occur. So if you kind of pull out the methods one by one and test them, you can catch that pretty easily. Right? That's the difference between passing that and failing that. But in this example, when I'm testing each method individually, I can figure out exactly the point at which it makes its first mistake. Whereas in the example where, in the example where I'm just sort of calling the overall method that tries to do all the work by itself, it fails by hanging. Right? And now you can understand the reason that it fails by hanging is that in the original code, this is kind of a fence post error, right? There's a boundary condition where it's going to get caught in this loop forever, because once it gets to d being exactly equal to 366, then this inner if statement will never execute, but d will never get decreased again. So that was the nature of the original bug. And trying to find and diagnose the bug from just a test that hangs when the whole thing is called, trying to actually exercise all of the different code paths, the nested if statements, the while loop, and stuff like that, that is a much harder testing problem than breaking out each individual little piece. Right? So what are the benefits that you get from breaking out the individual little pieces? First of all, the top-level function now tells a story. Right? The top-level function makes clear exactly what's going on. While there's more than 365 days, either peel off a year or peel off a leap year, depending on whether a leap year is true. That's it. The implementation of every one of those steps has now been pulled out into these so-called extracted methods. The extracted methods are short. They're easier to understand. Possibly most important, they are individually testable. So now, when the code makes a mistake, it's much easier to isolate where that mistake was made. Right? That's the nature of refactoring, is exactly to do this. By the way, if you look at the total number of lines of code, not counting the test, but just the refactored code, it actually got longer. Right? So here I have, depending on how you count, there's line 1, and here's the end. That's line 36. So it's more than a screen full of code, whereas here it's, 20 lines of code. So part of the moral of the story is that it's not just that less code is good in terms of accomplishing the overall function. However, what is the size of code that a human being has to comprehend at one time and for which you can write tests? That actually matters a lot. So the total amount of code on the right is more than double the total code on the left. However, each individual piece of code on the right can be understood almost in isolation. And by the way, if you wanted to test the top-level convert function, you don't have to understand how the interior functions work, right? You could stub them out if you wanted to test that it was doing the right thing. So you improve test coverage because now you can test the methods individually. You improve comprehensibility because each individual helper function is small. It does exactly one thing. It is quite clear from looking at each function what that one thing is. But you increase the total amount of code, right? So it's possibly counterintuitive that sometimes adding more code can make things more clear. What did we do in this case? We extracted the leap year method, or the leap year test into its own method. Then we simplified those nested ifs, right? The top-level function no longer has nested if statements because the nesting got pulled out into helper methods. The original version had variables all over the place. Those became instance variables of a class. So we're now hiding the instance variables inside the class. They're not even visible from outside. Every step of what I just did is available on GitHub, and there's like a README that actually explains the transformations that get you from each step to every subsequent step, and the tests, so you can actually reproduce the bug yourself. You can watch the test fail. You can do the thing where it hangs because you pass it one of the boundary values. But this is the general guideline of how you do this kind of refactoring. So what did we actually do in this case? We made a particular piece of code easier to read and easier to understand using some very simple refactoring. One of the most common refactoring methods that you'll probably find yourself using all the time is just extracting a method. You have a lot of code. You pull out pieces of it into helpers. Then you have to figure out, OK, well, now the helper needs access to certain variables that were part of the original code. How does it get access to them? Maybe you have to pass it, or maybe those can become instance variables of a class, and then they don't have to be passed back and forth. And now, by pulling it out, you have created a new point where you can test that method separately. You could argue that the bug that we just illustrated, which, like I said, was based on a real bug, if we had developed the method incrementally using TDD, things might have gone easier, right? If you actually started, suppose you started from the approach of writing just the top-level function that just said, if you started out from just the top-level function that said this, if this was the first thing you wrote, this is kind of a framing that serves as a blueprint for you as the developer to figure out what you need to do. In fact, I would almost think of it as like your first attempt at writing a method should almost be like pseudocode. It could even just be like comments saying, do this, do this, do this. And there shouldn't be more than 2 or 3 lines of do this, do this, do this, because each one of those lines is probably going to turn into a call to a helper method that does the real work. So the top level method is really just about orchestrating everything, right? It's about orchestrating the work of the various little helper methods. So my argument is that if you develop things in that order and you test as you go, you may find it easier to avoid these kinds of obscure problems that manifest as, OK, I've got a function that's got 3 deep nested ifs, and sometimes it does the wrong thing. How do I test that? And how do I figure out where in the function things are going sideways? Well, if you pull out the pieces into separate functions and test those, that usually gives you a very good clue. Also, if you go to the GitHub repo and follow the README instructions to replicate what I just did, it will tell you how at each step of that transformation you can compute, using the FlogGem, the ABC score and the cyclomatic complexity scores. And you can see that both of those scores go down as the refactoring progresses. So by the time we get to the end, we've got a bunch of little methods, each of which has a very low ABC score, low cyclomatic complexity, whereas in the initial version, you have a single big method with a quite high ABC score and very high cyclomatic complexity.